In this video, having discussed about the assumptions from the observation regarding the pure bending, we'll try to obtain stress and strain distribution of the beam under the pure bending. So here the approaches we're gonna take is following. So we'll, starting from a geometry, we'll first obtain the relationship between the radius of a curvature rho and normal strain epsilon, and from epsilon to sigma we're gonna use Hooke's law or material property, so that we obtain the distribution of strain, stress, and deformation on the pure bending. So here's the schematic of the geometry and the coordinate system that we're gonna define on the geometry. So the front view is as follows. This green plane is the neutral plane where we don't expect the length change under the pure bending, and when you look at the cross section, as I told you, we'll only consider symmetric beam, and the origin of y-axis will be defined to be the position of neutral axis, and we're gonna soon prove that the neutral axis go through the centroid point for pure bending. Okay, and based on the assumptions we made in previous page, the geometry of the beam after the pure bending with moment couple m can be written as follows. Okay, so here we define the rho as the radius of curvature of the this bending, and the cross section would slightly change it. Regarding the change of cross section due to the Poisson ratio, we'll just discuss it in later lectures. Today we'll focus on this main deformation. Okay, and here from simple high school or middle school geometry, we can quite easily see that the distance from this center O to neutral axis, which is the rho, if you multiply this rho with delta theta, due to the simple geometrical relationship between this arc length and the radius and the angle delta theta, then you can obtain this relationship. Now regarding the distance, like a y distance above this neutral axis, instead of rho, the distance here is rho minus y. So the delta s prime is smaller than delta x when y is larger than 0, can be written as rho minus y multiplied by delta theta. So this is the mathematical equations regarding the assumption we made in previous page. Now from this relationship we can obtain normal strain from the definition. So if we obtain the x direction normal strain epsilon x as a function of y, you can see that above this neutral axis it is compression. Below this we're gonna have the tension when m is applied in positive sign convention. So epsilon x can be written as delta s prime y minus delta s divided by delta s. Delta s is the original length before the deformation, and before the deformation, delta s used to be same as delta x. So instead of delta s, we put delta x here. And regarding delta s prime, which is the length after the bending deformation, you can write down rho minus y multiplied by delta theta. Okay, and if we subtract delta x from s prime, then what you're gonna get is on the numerator we're gonna have minus y delta theta, and if we divide minus y delta theta by rho delta theta, we end up having y minus rho. Okay, so until now we don't know what is this value. We're gonna make a connection between rho and m later, but suppose that we happen to know this law, then epsilon x max can be written as c minus rho. C is the largest distance from the neutral axis, and epsilon x as a function of y can be written as minus y over rho. And if we write down epsilon x in terms of maximum shear strain by combining this equation, you can make this kind of equations. Okay, so anyway, the implication here is the normal strain becomes larger as we consider the position farthest from the neutral axis, and interestingly, the strain changes linearly in terms of y position. Okay, and what you can see here is we are having additional complexity here when we are considering torsional loading. Shear stress and shear strain turns out to be linear function of rho. At the time, rho was the distance from the center, but in torsional loading we only have like I would say only one kind of shear stress, like we have only positive sign for torsional loading. After the torsional loading, regarding the shear stress, we only have a positive sign even though it's linear distance distribution. Here we have additional complexity. It's a linear distribution, but under pure bending it has both negative and positive sign of normal strain. I mean, both compression and tension occurs at same cross-sectional plane. Okay, that's the characteristic of bending deformation. And after obtaining epsilon x as a function of y, it's really easy to obtain sigma x as a function of y, because sigma x and epsilon y are connected through this Young's modulus E. Okay, so we already obtained the expression for epsilon x, which is minus y over c multiplied by maximum epsilon. And if you multiply E, you can obtain epsilon x in this way. Okay, now of course you can define this as these as maximum normal stress, and you can write down the stress in terms of y in linear function. Okay, so when we have this positive sign moment m, you can see that above this neutral axis we can have compression, below this we can have tension, and the distribution, if we draw the diagram, it looks like this. Okay, the size of arrow indicates the magnitude of stress at specific position. We have negative sign here, we have positive sign here. Okay, and this is the visualization of normal stress. Now until now we assumed that we somehow know the distance rho, and given this distance rho, and based on the assumption that all the cross-sectional area pointing at same point O prime after deformation, we are able to derive this geometrical relationship, and from geometrical relationship and the material property we can obtain the normal stress. Now it's time to connect the applied moment m and all those properties. Please see here we do not mention applied moment m up to these points, and it's time to make a connection between m and sigma x. So to make a connection between applied moment, this is a macroscopic moment that applied to entire plane, and make a connection with this m and the sigma x, we have to use two conditions. So for pure bending, because we don't apply any normal force, and the summation of infinitesimal force on that cross section must be 0, so that we don't have any axial loading. And if we consider the summation of all infinitesimal moment, then it must be summed up to be m. Okay, so that it satisfies the consistency between applied m and infinitesimal moment m. Okay, so let's consider the first condition. So actually from this first condition, we're gonna have some result regarding the location of neutral axis. Okay, so this is the front view of the beam under pure bending, and this is the visualization of normal stress. And if we take a look at the side view of this, and let's take infinitesimal area dA, and this infinitesimal area dA can be written as dy dz. Okay, and to satisfy the force applied in x direction, or xn must to be 0, then if you integrate this infinitesimal force on this infinitesimal area for entire body, it must be summed up to be integrate to be 0. Okay, and how to obtain this dx? And we already have the expression for sigma x in terms of y, and you do sigma xy and dA, this corresponds to dfx, and you have to consider summation over the entire cross section. Okay, so here I forget adding this. This integral is regarding entire cross section. So here what you can see here is after plugging the expression for sigma xy. Yeah, this is the expression. Now, yeah, this is constant and this is constant. You take out these outside of an integral, and you have this integral yda, and it must be 0. And because these are like a non-zero constant, this equation implies integral yda equals to be 0. Okay, then what does it mean? Yeah, this is the proof that neutral axis go through the centroid. Okay, so if you remember the center of mass expression, yeah, the center of mass must be defined as this expression. Now, if you consider centroid instead of mass, it must be defined as integral y dA divided by a. Now, our expression says that this integral is 0, which means that centroid is 0. Okay, so the implication of this result is that we define neutral plane as y equal 0, the origin of y-axis. Having defined the origin as the neutral plane, and after going through this mechanical equilibrium analysis, what this equation implies that integral yda must be 0, because we define y equals 0 as the neutral plane. The implication is that neutral plane corresponds to the centroid point. Okay, so this is the implication out of the first condition. Okay. Regarding the implication and the result of the second condition, the summation of imputational moment must be same as the macroscopic moment m, and we'll discuss about it in next video.